right, we are definitely in the situation of be careful what you ask for. So a number of students told me they needed more practice and repetition. So this week we are certainly getting as much practice and repetition as any of us could handle. All right, so our first review question this time is a linear approximation, and we want to find a cube. So we want to find the point nearby, and of course 8 looks like the logical choice. So f of 8 would be 8 cubed. So we want to do 64 times 8. And I guess we're going to come up with 512 as our point of tangency. And then f prime of x would be 3x squared. So our slope at 8 would be 3 times 8 squared. So 3 times 64 looks like 192. So our tangent line has the equation y minus 512 is equal to our slope, 192. Quite vertical, times x minus 8. So now what we want to do is find the point on the line by substituting x equals 8.2. So we will have y minus 512 equals 192 times 2/10, 0.2. So let's do some arithmetic, I guess. If I double 192, I will get a 4, an 8, and a 3, and then I need a decimal place. And then I would add 512 to both sides. So it comes up with 550.4. And you might be curious, so that's our approximation for 8.2 to the third is approximately 550.4. So I grabbed my calculator here as I paused the video. In the actual value, if I take 8.2 and cube it, the actual value is 551.362. So I just did this to check how close it was, so it's interesting that we're getting a very good approximation. All right, so another linear approximation practice. We're looking for the cube root of 8.2. So our function would be the cube root function. And our easy tangent point would be that f of 8 is equal to 2. So our derivative, this is the 1/3 power, subtract 1 from the exponent. So our slope, when we put 8 in there, if you want to rewrite this here, this is the derivative of the cube root of 8 squared. So we come up with 1/6. This one might be one we've done something. They're all similar. There's only so many problems that we come up with, so they all start sounding alike. So 1/6 x minus 8 is our tangent line. Let's back up there. Here we've got to square this, so it's true that the cube root of 8 is 2, but I need to square it first to become a 4, so this is 3 times 4. So let's get this fixed here. So this is not a slope of 1/6, but a slope of 1/12. All right, and now we're ready to approximate. So now we're going to let x be equal to 8.2. Y minus 2 is equal to 1/12. And I would do that as 2/10 or 1/5. So I like 1/60th on that side, so 2 and 1/60th. But you could certainly do that in decimal form if you want. So the cube root of 8.2, we didn't find that on the cube root curve. We actually found 2 and 1/60th on the tangent line. That would be a little bit of an overestimate because remember what our cube root function looks like. Our cube root graph in that area is concave down. At 8 it is concave down, so if you were asked the question you could say that this is an overestimate. But still should be a pretty good estimate. All right, logarithmic differentiation. Now, here's one where we wouldn't need to use logarithmic differentiation. We could use the quotient rule, or we could change these to negative exponents and do a product rule within a product rule, but neither of those choices sounds very fun. So what's the purpose of doing logarithms of both sides? Well, the log of a quotient becomes the difference of the logs. So if we wrote the logarithm of this quotient, we could immediately change it into the difference of the logs. And then in our denominator here, when we have this product, could you immediately, and I hope you would the next time that you do this, I don't need that multiply symbol there, I hope you would say, oh yeah, I remember that the log of a product is the sum of the logs. So we stretch this thing out, and now the next step I might as well bring down these exponents right away. So taking the logarithm of both sides when you have a complicated quotient or product rule might be something that you want to try. All right, so here, let's be careful about signs. The log of a product would be the sum of the logs. So I can bring down the exponents. Let's get that as a 1. So the log of a product is the sum of the logs. If I could write x minus 1. And then I brought down the exponents right away. This was what I wanted to be careful about, that this minus sign has to apply to both of those. So if they're in the denominator, the terms in the denominator, shouldn't they both be negative? When you're dividing, don't you subtract exponents? And logarithms are exponents. Okay, did this really simplify our derivative? Well, quite a bit. Now watch how simple to do implicit differentiation. The derivative of natural log of y is 1 over y, chain rule on the y. The derivative of natural log of a glob is 1 over the glob times the chain rule on the glob. And couldn't you put that together right away if you're thinking about it? Okay, now I'm going to distribute that minus sign and put in on each term. So here the derivative of the natural log of that glob is 1 over the glob times the chain rule on the glob. And then this minus sign is distributing here. So the next one's also negative. Keep the 5 in front. The derivative of the log is 1 over the glob times the chain rule on the glob. So really, isn't that a whole lot simpler than doing a product rule inside of a quotient rule? So here we have 16x to the third over x to the fourth plus 1 minus 6 over 2x plus 1 minus 15 over 3x minus 1. All right, and I just noticed as I proceeded here that I copied this exponent wrong. So do you follow my eraser here? This was x squared and I just copied it wrong. So that would be a squared, and then that would change our chain rule would just be a 2x. Sorry, gentlemen. And then this should be a 8x. And one last fix here. That was x squared. All right, we haven't quite simplified it yet here because we want dy dx all by itself. So we want to multiply both sides by y, and technically here we can write the right-hand side with no y's at all. We would like it to be in terms of x's. So now we can put our y back to the original So y is equal to the original glob. And then we could distribute this all the way through, but it's not going to simplify easily. And chances are, if you were using this problem, you might simply, in your next step, want to say, well, what is dy dx when x is equal to 2? And then you would just have to clean it up after you do your arithmetic substitution. So taking the logarithm and then using our products of logs made that problem easier. We could avoid the product rule and the quotient rule. Number 4, though, is an example where we must use natural log of both sides because we have a variable in the exponent and a variable in the base. So we must take the natural log of both sides. So this is going to look confusing because we're going to have the natural log of a natural log. And notice I already moved this exponent down in front. All right, so this might look like a strange problem to us at first. So our implicit differentiation, 1 over y with a chain rule on the y. And on this side, we have a product rule. Here's our u function and our v function. So we start out with a product rule, and then this is going to be weird, and this next one we're going to have to do a chain rule because we've got a log inside of a log. All right, so we want to take our u function, cosine x, times our derivative of v. So let's think carefully about that. The derivative of this natural log would be 1 over its argument times the chain rule on its argument. So there's our v prime plus our v term times our u prime. The derivative of cosine x is negative sine x. All right. And then we want to move our y to the other side. And when we move the y to the other side, we're going to rewrite it in terms of x only. So we're going to go right back to the original. So instead of y, we're putting it back in from the original. And is there much I can do with this? I could put cosine in the numerator and x ln of x in that denominator. And then I'd have a minus sine of x times ln of x. And I think that will do it. All right. We have a particle moving along a horizontal line with a position function measuring in seconds and in feet. All right, velocity is our s prime of t. So velocity is the derivative of position, 3t squared minus 12. Acceleration is s double prime, the next derivative. So v prime is the acceleration, and that would just be 6t. And when is the particle moving in the positive direction? That would be the same as asking when is it moving to the right. So we want to find out when is v prime, or when is velocity positive. So first let's find out when velocity is 0. So we could factor that 3, and then we'd have t squared minus 4. And that factors as t minus 2, t plus 2. So there are two critical numbers. Our critical numbers, it could change directions at -2 and at +2, but notice back in our problem it said we're only interested in times greater than 0. So we're only interested in the interval starting at 0. So instead of going from -2 here, we're going to start at 0. All right, so we want to test our intervals here from 0 to +2. Think of putting a number in here that's between 0 and 2, like 1, and we'd have a 3 times a negative times a positive. So the velocity is negative. And then once we choose a number bigger than 2, both of those parentheses will be positive. So again, when is it moving in the positive direction? That would be when its velocity is greater than 0. Oops, sorry about that. So let me rewrite it. It's moving to the right or in the positive direction on the interval from 2 to infinity, since v of t is greater than 0. And if you can do all that work in your head, that's fine. You only need to justify your answer. You'd have to see the factored form, I think, to do that. When is the particle speeding up? All right, so now we want to find out when are velocity and acceleration both positive or both negative. So speeding up means acceleration and velocity are going in the same direction. So let's look at our acceleration function. Our acceleration function is 6t. So a of t is less than 0 only if t is less than 0. But here, remember, we're not interested in negative numbers. Remember that we're starting at time 0. So a of t is greater than 0 the entire time that t is greater than 0. So acceleration is always positive. So when is it speeding up? Our velocity was positive after 2, and our acceleration is always positive. So they are in the same direction or same sign after 2 seconds. So on 2 to infinity, v of t and a of t are both positive. So I guess we can say it's speeding up on that interval of 2 to infinity seconds because v of t and a of t are both positive. All right, find the total distance traveled in the interval from 0 to 3. So we need to find out where it is at its endpoints. So what is s of 0? Its position at time 0. And our critical number in the interval here, -2 was a critical number, but it is not inside our interval. So we only have one critical number where it changed directions. And then let's find out where it ended up with at s equals 3. Just changed. And when s is equal to 3, let me repeat here. I had just changed pages on you. Hopefully I paused the video in time. Is that a -6 feet? All right, so let's find out our total distance. So from +3 to -13 looks like 16 feet. And then from -13 to -6 would be 7 feet more. So it looks like it went a total distance of 23 feet. All right, from a graph of the position, when is the object slowing down? So we want to know when acceleration and velocity have opposite signs. Okay, and here, I think I've just moved things. This s here is supposed to be covering this up, so if this is a position function, I think is what it says on your copy of the sheet. So if this is a position function, let's think about velocity. Velocity is the first derivative, so the slopes of s here would be positive, so velocity is greater than 0. And then the slopes here are negative, so the velocity is less than 0. And acceleration would come from concavity. This looks like an inflection point to me. I think the graph is concave down from 0 to 2, so I would say that the second derivative, acceleration is the second derivative, is negative when it's concave down, and the second derivative of acceleration is positive when it's concave up. So slowing down would mean that acceleration and velocity have opposite signs. So let's look carefully there. Where do they have opposite signs? We've got a positive and a negative between 0 and 1. Velocity is positive, but acceleration is negative. And then it looks like from 2 to 3, the velocity is negative, but the acceleration is positive. So on 0 to 1 second and 2 to 3 seconds, it slows down because acceleration and velocity have opposite signs. And I think that justifies it. All right, a second derivative by implicit differentiation. So let's do the derivative with respect to x. So we do not need a chain rule on the first term, but we do need a dy dx chain rule on the y term equals 0. Let's solve for dy dx. We'll have a negative 6x to the 5th divided by 6y to the 5th. So there's our first derivative. Cancel those 6's. Press right on to the second derivative. So we got to do a quotient rule. Low d high minus high d low. This is where we need our chain rule. Derivative on y requires a dy dx all over the denominator squared. So this is our first substitution right here for dy dx. So let's get that in there, and we'll rewrite these terms. Minus 5x to the 5th, y to the 4th. And this is where I'm going to substitute our slope, our dy dx. And I bet you've already seen these same patterns happening many times now. This y to the 4th can cancel, but we'll still have one y left down there. So we will have to multiply by y over y. And don't forget to distribute times both terms. Whoops, sorry. Let's clean that up. We'll continue up here. So we could, and you could right away, by the way, if you wanted to take out 5x, well, but that's probably not a smart idea. We're going to factor some more later anyway, so let's leave it. Y to the 5th, and then here we'll have a positive because we've got negative times negative. So we've got positive 5x to the, I can't read my own writing there. How about x to the 10th? And this y, I said I forget to distribute, and I still forget. That y times a y should be a y to the 6th, and then over y to the 11th. All right, so now if we factor a negative 5x to the 4th out of the numerator, we're not factoring the negative was already out there. We're factoring 5x to the 4th, so we would have y to the 6th plus x to the 6th. We're grateful to see that because from our original equation, x to the 6th plus y to the 6th in this case is 1. So we can substitute 1 into that numerator, and here is our second derivative answer. So this negative answer. All right, An important question here. Hopefully we still have your attention. This is testing several things here in this problem. So if you need a break, pause and come back to it, because this could be a very likely test question. So what you're doing here is testing your derivatives. So we're going to find p prime at 2. So look at the rule for p prime. That would require a product rule. So by the product rule, we would write that p prime of x is equal to the first function times the derivative of the second plus the second function times the derivative of the first. And now we want to find out what p prime of 2 is. So we want f of 2, we're going to read these from the graph, times g prime of 2 plus g of 2 times f prime of 2. So for f of 2, we're just reading the y coordinate. So f of 2 looks like a 0. So we really don't care what g prime of 2 is in that case. But just to make the point here, g prime of 2 would be this slope of this tangent line, and that would happen to be a 2. And then g of 2, I covered it up right there, g of 2, 1, 2, 3, 4, and f prime of 2 at 2, f prime has a slope, look at the tangent line, of -1. So 0 minus 4. So our answer for question A. So this is all question A, p prime of 2. All right, I don't know. Let's see if I agree with that answer. F of 2, oops. F of 2, how about that? F of 2, that's f of 3, isn't it? What's f of 2? Right there. I read f of 3. F of 2 is 1. Okay, so I had notes next to me as how I caught my error. So this is 2 minus a 4. All right, so part B is, this is a division line. So part B is testing the quotient rule. So I'm going to run out of room quickly here. So our quotient rule for part B, so q prime of x, the quotient rule says to take the low function times the derivative of the high function minus the high function times the derivative of the low function all over the low function squared. And now we want to do that value specifically. We want to do q prime at 2. So we're going to read those values again, and we just did them a minute ago. So g of 2 is a 4, and f prime of 2 was a -1, and f of 2 was a +1, and g prime of 2 was a 2. All divided by g of 2 was our 4, and we want to square that. So our numerator looks like a -4 minus 2, so -6 over 16. So how about -3/8 for part B? All right, part C is our test of our composite rule. So I'm going to scroll and do that over here. So C prime, when we have a glob inside a glob, we do the derivative of the outer, leave the inner glob alone, times the derivative of the inner glob. And now we want to find that value, specifically at 2. So let's write this here so that we don't miss any steps. G of 2, if I erase my points here, G of 2 was our value 4. So we want to do f prime of 4 now times g prime of 2. So f prime of 4, we haven't done that one yet. 2, 3, 4. So we're looking for the slope right here. So from a grid point to a grid point, oh, here's a grid point, sorry. up 3 over 1. So it looks like we have a slope, a rise over run of 3. And g prime of 2, we had already done that one. That was 2. So we'll come up with a 6 for part C. So those are really important questions because they're good, quick test questions to see whether you understand product rule, quotient rule, and chain rule. All right, let's see if we can get this thing finished up here. Here's a product rule with a chain rule inside it. So we got to think of this as u and v. So our y prime is our first function times the derivative of arctangent is 1 over 1 plus the glob squared times a chain rule on the glob. So there's our u v prime plus our v term, arctangent or inverse tangent, times our u prime, and the derivative of x is 1. And we could move the 4x to the numerator, but nothing else required here. So I think that would work fine. And in number 10, we have some implicit differentiation. So again, we have a u times a v product rule here. So we have the first term, u, times the derivative of e to the y is e to the y, with a chain rule on the y. That would be an easy one to forget. Always a chain rule on the y. So there's our uv prime. We're not finished with the product rule. So now we've got to do our v term times our u prime, which is the derivative of x is just 1. On the right-hand side, the derivative of y is 1 with a chain rule on the y. And the derivative of negative 1 is 0. So we've got two terms here that have a dy dx. And both of them are positive, so it doesn't make much difference. We might as well keep the e to the y term on this side and move the dy dx terms to this side. I think it would look like that. So, oops, sorry. So when we divide e to the y, sorry, I keep hitting that page change there. When we divide by this binomial, I think we're good. All right. So, finally, enough review.